Right, so the Ka expression is useful because we can use it to find the pH of a weak acid. We're looking at weak monobasic acids here. So here's the dissociation, here's the Ka expression. Now we're going to make some assumptions or approximations here. Weak acids are very, very weak. Most of the HA, the acid over here, does not dissociate. So we say that the what it was originally, the undissociated HA, equals what it is at equilibrium. Now that's not really possible, but the change is going to be so small that mathematically it's not going to make much difference. Also, what we can assume is that for every one H plus made, you make one A minus. So at equilibrium, the concentration of H plus equals the concentration of A minus. Now that's kind of ignoring what was happening with the water in solution. But again, the difference would be so small mathematically, it's not worth looking at. So, what can we use this for then? Well, it just means that we've got less unknowns in this equation when we want to find H plus. For starters, if these two at the top equal each other, rather than having H plus times A minus, we can just make it H plus squared. And the HA here, we can just use what it is at the beginning of the question, of the beginning of the problem, because we just use the undissociated one here. So we want to find H plus, so we're going to make that product of the equation. So I'm going to times by HA, so H plus squared equals Ka times HA. And then I'm going to square root it to just get H plus by itself, so H plus equals a square root of Ka times HA. Once you've got that then, if that's H plus, let's put it into the pH equation, substitute it in, so the pH equals a minus log of the square root of Ka times HA. So if you know the concentration of the weak acid at the beginning, you know its Ka value, you can find its pH. So here's an example. What is the pH of a 0.1 moles per dm cubed methanoic acid solution? And here's its Ka value. So I stick the Ka value in, I stick in the concentration, times it together, square root it, minus log it, and I get 2.37. So what's the limitations of this? Well, the biggest limitation is when you have a stronger weak acid. I don't mean a strong acid that completely dissociates, just a weak acid that dissociates more than some of the other weak acids, because then it's kind of pushing it really to say that at equilibrium the concentration of HA equals concentration of what it was undissociated, and so mathematically that starts to fall down then. It's a problem. Benzoic acid has a pH of 5. What is its concentration? So when we get the pH, find the H plus, 10 to the minus power 10 to the minus pH. So the pH is 5, you do 10 to the minus 5, that gives you H plus. We saw just a bit now that H plus squared over HA equals Ka. So I can take this in here, 10 to the minus 5, and stick it in there. Okay. But what I'm trying to find though is HA. So I want to know the concentration of the acid. So that's just been rearranged there. HA equals H plus squared over Ka. So, putting the values in, 10 to the minus 5 for the H plus, square it, divide by the Ka, and you end up with that value there. Okay.